So shortest job first is the best known scheduling algorithm as of now, but there is a small problem with this. The problem is it is the best one, but you cannot implement it. What is use of it, isn't it? It is the best one for sure, but then you cannot use it, right? So what is the reason? See this. Now shortest job first has both advantages and disadvantages. Advantage is that if you implement this for any process, that will lead to maximum throughput. Throughput means the number of processes that are finished per unit time is called throughput. Therefore SJF advantage is that it has maximum throughput, but the problem is okay, what is throughput is this. You see the schedule, which means when you started the first one and when you finish the last job, that entire thing is called schedule, and within this time you see how many processes have completed, right? Then that is nothing but the throughput. For example, if you write like this, the schedule is the Gantt chart. Let us say this is the point where you started the first one. Maybe at 0 nothing is available. At one time you started the first one and then you finish the last one here, right? This entire thing is called length of the schedule, and now in this length of the schedule you count the number of processes that you've completed, right? Then after finding it, then the throughput is nothing but number of process per unit time, which means take the number of, let us say you have completed six process in maybe 60 units of time, then the throughput is 1 by 10, 0.1 process per second. That is how you come to know about the throughput, right? Now the overall throughput of every scheduling algorithm will be same, but here what happens is at any point of time, if you stop the schedule and then you count the throughput, it is going to give you the best one, which means at this middle point, at this point, if you stop it and if you see the throughput, this will give you the best thing, because many of the process will get completed as early as possible. It is simple. Why do we get the maximum value of throughput at any point of time is we are trying to finish as many jobs as early as possible by taking the shortest burst times. If I follow this strategy, obviously many processes will get finished as early as possible, isn't it? Fine. Therefore it will have maximum throughput and minimum average waiting time and turnaround time. You can take an example, and after I finish all the scheduling algorithms, you do one thing, take an example and say it, that for any example this shortest job first is going to give you the minimum average waiting time and average turnaround time. These are the two characteristics which are required by any scheduling algorithm in general. Anything you take up, if these are the two must, so this is the best one possible, this is the best scheduling algorithm possible. But the problem with this is starvation to longer jobs. Okay, fine, we can cope up with this, but the main problem is it is not implementable because burst times of process cannot be known ahead. This is the problem. You cannot know how much time does a process require, so you cannot implement it practically. So since we cannot implement SJF, we are not going to leave it completely. What we could do is, since we are not able to know the burst times exactly, we will approximate it. So we are going to approximate it like this. So shortest job first with predicted burst times, which means we predict the burst times and we start off. So we don't know for sure that we are right, but then we can predict the burst times when we can start off. It is like approximate algorithm, not the actual algorithm. See, whenever it is not possible to implement an algorithm, then what we do is the closest approximation. Then the solution will be not the optimal one, it will be the closest to optimal one, right? So here what is that we are doing is we are trying to predict the burst times. Now there are two ways you can predict the burst time. One is static. Static means you are not going to see anything else. Once you fix it, it is going to be like that. And other is dynamic. Dynamic means it will continuously keep on changing while you are performing the schedule, right? And now static means process size. It is based on two things. One is either you could base on process size or you could base on process type. And dynamic means there are two types. One is you can base on simple averaging, and other is exponential averaging, or it is also called as aging. Now I'll talk about the static first. So the first technique is process size. So depending on the process size, if you guess the burst time, that is the static one. What does it mean? So if a process is depending on the process size, we count the size of the process and then we see if this size matches with any process which we finished earlier, and then we take that earlier process and we examine it, how much time it has taken, and now we predict that maybe these two could take the same time. It is actually wrong. I mean, not exactly right. Sometimes it works, but it is simple one, right? So how it works is, see this: if there is a old process which has already finished, whose size was 200 kb, and if it took 20 units of time, then the new process, if its size is 201 kb, it will also take 20 units. That is what I guess, because these sizes are actually similar. But then it is difficult, because even though the sizes of the process are similar, their nature might be different. Depending on the nature, they might be different, right? So it is really difficult in that way, or it is simplest one to implement it, but then it is not actually, I cannot say anything, like it is not always right, it is not always wrong. Sometimes it might be right, sometimes it might be wrong. Therefore, next method is based on the type of the process, we can guess the burst time, right? So it is up to you. You can fix some time like this, depending on the type of the process, if it is operating system process or user process. What is operating system process is, whenever operating system wants to run some code, that is also a process, right? For example, schedulers are all process, dispatcher is a process, and process manager is a process, right? So resource manager, all of these are processes. Whenever operating system wants to run a process, then that will be given some time. So generally they run faster, therefore 3 to 5. And then whenever user has a process, there are various types of process. One is interactive. Interactive means you want to continuously interact with it, like gaming, right? Another one is foreground. Foreground means that will be running in the foreground. Background means it will be running as a demo, it will be running behind, right? Now depending on that, you can assign some times, because every process is not going to take the same time. Depending on the type of the process, you can come with the burst times. Anyway, once you predict the burst time, then you can go with shortest job first. So if your prediction is right, if your prediction is exactly right, then you'll get the best possible result from the SJF. But then the prediction is always not right, isn't it? So there will be some many things involved, right? So these two methods are work this way, but the best methods are dynamic methods. We shall see the dynamic methods now. Now one of the dynamic methods to predict the burst time is simple averaging. It is, in simple words, it is like this: if you are taking up a process now, then its burst time will be predicted as the average of all the process completed till now. Which means, if you are talking about the process P5, then I'll see 1, 2, 3, 4 process, and I'll find out their burst times, because they are already done with their execution. Then I'll take the average of this, and I'll predict that the fifth process is going to take that average time, right? So how is it going to be implemented? If I have n process, P1, P2, so on Pn, then let Ti be the actual burst time, which means that small ti is the actual burst time. Then tau I denotes the predicted burst time. Then how can I predict the tau I, which means the next process burst time is, it will be taken as the average of all the processes which got completed. That is why it is 1 by n into this one. Got it? It is a simple one, right? Dynamic, we shall see it. Now the next dynamic method to predict the burst time is exponential average. So exponential average is like this. See this? To predict the time of n plus 1th process, we are going to take alpha into actual time of the previous process plus 1 minus alpha into the predicted time of previous process. Which means when you are at process P5, then I am going to depend on two things. One is what has happened to P4 actual time, and then what we predicted for P4, right? So we are going to take the average of these two. I mean, some not average, some kind of it. So here alpha is called as smoothing factor. So it need not be in some number. I mean, it need not be 0 or 1. It can be anything. So how does this formula behave is, I'll just tell you. See, now if you want to find out the prediction for Tn plus tau n plus 1, then I want to take these two, right? Then in order to find, this one can be found out by running nth process, but this one is the guess, isn't it? Then what is tau n? According to this formula, tau n equal to alpha into Tn minus 1. In place of n, I am putting n minus 1 plus 1 minus alpha into tau n minus 1, right? Let's call this equation 2 and let's call this equation 1. Now you can substitute 2 in 1, equation 2 in equation 1. Then what do we get? Then tau n plus 1 equal to alpha into Tn plus, now this entire thing you can multiply it out, right? So 1 minus alpha into Tn minus 1 plus 1 minus alpha square into, I'm just writing here, tau n minus 1, isn't it? So if you look at this, therefore the next prediction actually is depending on the previous time as well as the job, previous earlier to this, and then the prediction for this job as well. So if you could keep on expanding it, you will even find out that the next prediction depends on all the previous history. History means what has happened to all the process till now, as well as what is your initial guess, which means like this. If you keep on extending it, can I just extend it? Alpha into Tn plus 1 minus alpha into Tn minus 1 plus, if I substitute this one, 1 minus alpha square into, if I substitute this one in place of tau n minus 1, if I substitute it, then what I get is 1 minus alpha square into Tn minus 2 plus 1 minus alpha cube into tau n minus 2, isn't it? Therefore you can see that it can be extended this way. So the next process prediction depends on all the previous processes plus, see this, all the previous process plus the initial guess. This one will go on till the initial guess, which is the guess for the first one, which is tau 1. So it is going to go till that tau 1 and it is going to stop there, right? So this is how this exponential method works. If you want to understand it better, let's solve this question. Okay, one more thing, this alpha is called as smoothing factor. Smoothing factor means what is the weightage that you want to give it to the previous process and what is the weightage that you want to give it to the remaining history, right? So now depending on alpha, your values will change. If you believe that the last process is actually right, then give alpha high. If you give alpha very high, then the next process time will be equal to the earlier process time, which means if I put alpha equal to 1, that is the highest value possible, then tau n plus 1 will be equal to Tn. So this means that the next process burst time you are predicting as to be what happened to the last one. If you put alpha equal to 0, then what happens is tau n plus 1 equal to tau n, which means whatever you predicted last time, you are staying on that, you are sticking to that, which means you are thinking that your prediction is always right. So if you put alpha equal to 1 here, it is very dynamic, which means depending on the previous process you are going to change. And if you put alpha equal to, so one second, in case if you put alpha equal to 0 here, then you are always remaining static, which means whatever your initial guess is, tau 1 is, you are just staying there. So depending on the alpha, the dynamism of this algorithm depends. Are you understanding it? See, if I put alpha equal to 1, then what happens is tau n will become Tn, because this factor will become 0, which means the next process burst time you are predicting that it will be equal to the earlier process burst time, only one process. You are very dynamic, right? And in case if you put alpha as 0, then you are thinking that your initial guess is right. And what is this one? So if you see this and go back and see this, it will trace out to be tau 1, which means whatever you guessed for the first process, that is going to be applied for all the process, which means static, right? So now let's see the problem, you'll understand it better. Now alpha value will be always given in the exam. Alpha is called smoothing factor, right? Now alpha will be given in the exam and the remaining factors will be given like this. If alpha equal to 0.5 and tau 1 equal to 10. So tau 1 equal to 10 means the initial guess I am guessing is 10 units. Then the next 4 processes, actual burst time turned out to be T1, T2, T3, T4, 4, 8, 6, 7, which means this is what I guessed, but the actual burst times of 4 processes turned out to be this. Then what is the next one? So how can you do this? I guess substitute in that formula, right? So one is you have to find out the tau 2. So how can you find out the tau 2? it is alpha into tau 1 plus 1 minus alpha into what has happened to the first one, t1 plus 1 minus alpha into tau 1. So alpha is 0.5, therefore 0.5 into t1 is 4 plus 0.5 into tau 1 is 10. Then the average of these two is 14, means 7, right? And now the next one, tau 3. So tau 3 is going to be alpha into t2 plus 1 minus alpha into tau 2, and tau 2 is this one, right? Then what is it? 0.5 into t2 is given as 8 plus 0.5 into 7. So therefore it is 7 plus 8 by 2, which is 7.5. And now tau 4. Tau 4 is alpha into t3 plus 1 minus alpha into tau 3. Then what is alpha into t3? It is 0.5 into t3 is nothing but 6 plus 1 minus alpha means 0.5 into tau 3 is nothing but 7.5, right? And now you take the average of these two. It is actually 13.5. Average of 13.5 is, I think, 6.75, right? Okay, I'll again check it. And now finally tau 5. So anyway, don't worry about the numbers, you please do it. Tau 5 is nothing but alpha into t4 plus 1 minus alpha into plus 1 minus alpha into tau 4. Then what is it? What is t4? t4 is given as 7, which means 0.5 into 7 plus 0.5 into tau 4 is 6.75, right? So finally the answer for this one is 6.875. This is the answer. Okay, so that is how you could solve the questions. Anyway, practically we don't use it much. So the most practical algorithm is round robin. We shall see it.